Hello and welcome to my science tutorials. In today's video, we are going to be talking about the reactions of alkenes. Before we begin, if you are new to my science tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. Now, the alkenes have what? The carbon-carbon double bond. They are known to have the carbon-carbon double bond. And then they are considered the gateway functional groups. That is, their reactions normally leads to the formation of what? Other functional groups. So we can convert an alkene to other functional groups like what? An alkyl halide. So we can get an alkyl halide from what? An alkene. We can also produce what? Epoxides from alkenes. We can also produce what? Aldehydes and ketones. Aldehydes and ketones from alkenes. We can also produce what? Carboxylic acid, acids, and many other functional groups from reacting what? Alkenes. Now in this tutorial and other subsequent tutorials, we will be covering the most common reactions, including their mechanisms, reactivity, orientation, and then what? Stereochemistry. Okay, now because single bonds are made of what? Single bonds are sigma bonds. They are more stable than pi bonds, and then mostly they do not react. But then the double bond that we have over here, one is what? A sigma bond, one is a pi bond. Now the pi bond, the electrons within the pi bonds are loosely held. Okay, so in alkenes, because of these loosely held electrons found in the pi bonds of the alkenes, they tend to undergo reaction because the electrons are what? Are delocalized, and then they can move around. Alright, alkenes undergo three types of reactions. We have first of all, we have the addition reaction. We have the addition reactions. We have the elimination reactions. Elimination reaction. Then we have what? The substitution reaction. Alright, now for the purpose of this tutorial, we are going to look at types of addition reactions that alkenes undergo. So if we have our carbon-carbon double bond over here in the middle, okay, now if we react the alkene with what? With water. If we react an alkene with water, we call this reaction what? Hydration reaction, or acid catalyzed hydration. And then this reaction leads to the production of what? An alcohol. So we have our hydrogen here, then we have our carbon, then another carbon with what? OH attached to it. So this is what? Our alcohol. Okay, this same alkene, if we react it with what? Hydrogen gas, okay, we call this reaction what? Hydrogenation reaction. And then we produce what? A normal alkene. So we have this, then with the hydrogens being added over here, so this is our alkene. And then remember, this is a type of what? A reduction reaction. Okay, now if we react this same alkene with what? HOOH, okay, we call this reaction dihydrosilation or dehydrosilation reaction. And this reaction leads to the production of diols. That is, we have two OHs attached to the carbons bearing the double bond before the reaction occurs. So we have the diols. Alright, now this same alkene, if we react it with what? Oxygen gas, we call this an oxidative cleavage. This is an oxidative cleavage, and then we get product like this. So it means the double bond over here will be split into two, and then oxygen will attach to both of them. So this plus the second carbon also having the double bond O here and then over here. So we can either produce what? Aldehyde over here. Aldehyde and ketones, depending on the starting material or the alkane that we have. So oxidative cleavage is just breaking the double bond over here and then adding oxygen to both. Alright, now this same alkane, if we add just oxygen to it, we call this epoxidation. That is, we have the carbon here being attached to the oxygen over here. So if we have any compound of this form, this is what we call the epoxide. Okay, that is just adding oxygen to an alkane. Now if we add what? A halogen to an alkane, we call this halogenation. Halogenation reaction will produce what? A haloalkane. Okay, so we have our carbon here, then we have our halogens being attached to the carbons. Alright, so when we add what? HOX to an alkane, we call this what? Halohydrin formation. The halohydrin formation, and then we get the halohydrin, which is of the form, we have halogen attached to it, and then we have OH attached to the two carbons bearing the double bond before the reaction occurs. Okay, so if we add HX, a hydrogen halide, we call this hydrohalogenation reaction. So this is what? A hydrohalogenation. So we get a halohydrin. So we have this with our H over here, and then carbon with an X, or our halogen over here. Now this same alkane, if we add what? CH2 to it, we call this cyclopropanation. So cyclopropanation reaction, and then we have the product looking like this with the new carbon over here, within the two hydrogens attached to it over here. Okay, so these are some of the few reactions that alkanes tend to undergo, but this is not all. We have other reactions such as alkoxymmercuration demercuration, oxymercuration demercuration, and then the formation of carbenes, which I've not talked about over here. But just so you know, these are not all the reactions that alkanes undergo. These are some of the addition reactions that they undergo. So we have the electrophilic addition reaction, the substitution reaction, and other reactions as well. So you might want to go and search the internet for other reactions of alkanes. But in the subsequent tutorials, we are going to be looking at all of these reactions one by one and into detail. Now, another thing to note is the fact that during this illustration, I'm not taking into consideration the regiochemistry and then the stereochemistry of the reactions. That is to say, the regiochemistry is the what? The orientation of addition of the reagent, meaning which part of the reagent adds to which part of the double bond. Okay, so some reactions are what? Regioselective, that is, the hydrogen attaches itself to a specific carbon that is either less substituted or what? The most substituted, or the halogen that we have attached itself to the most substituted or the less substituted reaction. So some reactions what? Are regioselective, and then other reactions are what? Stereoselective. So by stereoselectivity we mean what? The 3D orientation. So if let's say we are adding, let's say, water to an alkane, for instance, depending on certain reaction conditions, you can add the OH through the front side of the reaction, but then you have to add a hydrogen through the back side of the reaction. Okay, so that is just a brief example of what stereochemistry means. But during this illustration, I did not make use of what stereochemistry and then regiochemistry, and also the reaction conditions, I did not state any of them, so take note of that. Alright, so with this brief introduction to what the reactions of alkenes looks like, we want to look at the first reaction of alkene. So the first one we are going to look at in this tutorial is what? Hydrohalogenation reaction. So hydrohalogenation. Now the hydrohalogenation is just adding what? HX to an alkene. Alright, so like the name suggests, this reaction involves the reaction of a hydrogen halide, which is of the form HX, and examples are what? Hydrogen bromide, HCl, HI, and other examples, okay, to an alkene. So when we add a hydrogen halide to an alkene, we call the reaction hydrohalogenation. Okay, so let's have a look at an example and have a feel of how this reaction looks like. So assuming we have the alkene CH3 bonded to another CH3, then we have doubly bonded to what? Another carbon bearing hydrogen, and then CH3. Then we are adding what? HBr to this. Now, under normal circumstances, this bond is going to break, and then the hydrogen will be attached to one of these carbon, and then the bromine will be attached to another carbon. So there are two likely products that are supposed to be formed. So we can have our CH3 attached to carbon CH3 here, then we have our bromine attached over here, then we have our second carbon with the hydrogen, then we have the CH3, then we have the hydrogen over here. Okay, so this is the bromine being added, and then this is the hydrogen too being added. Or we can have the CH3 attached to the carbon bearing the other CH3, then we have the hydrogen attached over here, then we have the other ones over here, so CH3, and then we have our bromine over here. So these are the two likely products that are formed when we have hydrohalogenation. Now, from experiment, it is observed that what? Only this product here is the only product formed. And this is not formed. So why is it that only this product is formed? Okay, it turns out that the hydrohalogenation reaction is what? Regioselective. By regioselective, we mean what? The position where the hydrogen is going to attach itself to one of these carbons is determined by the reaction, and then the position where the bromine is also going to attach is also determined. So the regiochemistry or the regioselectivity of this reaction follows the Markovnikov addition. That is to say, the hydrogen attaches itself to the carbon bearing what? Or the carbon that is less substituted. If we look at these carbons, we have carbon 1, carbon 2. Let me use another color for this illustration. Let me use green. So we have carbon 1 and then carbon 2. We can see that carbon 1 has what? 2 alkyl groups, 1 and 2. Then carbon 2 has only 1 alkyl groups. So in terms of what? The number of alkyl groups that carbon 1 and carbon 2 has, carbon 1 has more alkyl groups, and hence it is what? More substituted. So when this reaction occurs, the bromine will be attached to what? The most substituted carbon, and then the hydrogen will be attached to the less substituted what? Carbon. And if that happens, we can see that this is the only product that will be formed. Now let's look at the mechanism of this reaction to appreciate what actually happens when this reaction is occurring. Okay, so let's have our CH3, C bonded to another CH3, then we have the double bond CH, then CH3, and then we are adding our hydrogen bromide to it. Now in the first step of this reaction, we have the protonation of the double bond to form a more stable carbocation. So like I said, the double bond over here is an electron rich center, and then this is what? This bond, the hydrogen over here has a partial positive charge, and then the bromine has a partial negative charge. So the double bond over here has an electron, so it will be attracted towards the positive charge. So the hydrogen will attack, the double bond will attack the hydrogen, okay, and then breaking the electrons onto the bromine. So we have this CH3 here, then we have this carbon, then we have our CH3 at the top, then this double bond becomes a single bond, and then we have CH, the H over here, then we have the other CH3 attached. Now where does this hydrogen goes? Okay, like I said, this reaction is regioselective. That means what? It follows the Markovnikov addition. So by Markovnikov, it means the hydrogen will go to the less substituted carbon, then, and the less substituted carbon between these two carbons is this carbon over here, because it has what? There's one alkyl group attached to it. So the new hydrogen that we are adding is what we have over here. So let me use a box to cycle it, okay? And then when that happens, because this alkene, this carbon over here is now having 3 bonds, it will now assume what? A positive charge, okay? Now that it has assumed a positive charge, this is called what? A carbocation. So this is a carbocation. Now let's look at something. We can see that this carbocation, the carbon over here bearing the positive charge, is attached to what? 3 other carbons around this. So this is what? A tertiary carbocation, okay? So now that we have the tertiary carbocation being formed, we still have the bromine anion in solution. So it will now attach itself, it will now attack the carbon bearing the positive charge, and then we get our product, which is what? CH3, C, CH3, then we have our bromine here, then we have CH, then CH3, then our hydrogen over here. So this is our product, okay? Now someone will say, what happens if the hydrogen is attached to the more substituted carbon? Now let's look at what happens if that happens. So let me use another color. Okay, so in case the hydrogen goes the other way around, okay, so we are going to have this, then we have our carbon attached to CH3, then our hydrogen will be attached to the more substituted carbon. Note, this reaction is not feasible, okay? Not feasible, which means it does not happen, but just for demonstration's sake, I'm going to do it, okay? So we have our carbocation being formed on this carbon, and then we have our Br minus in solution, okay? So we can see that when the double bond attacks the proton, the hydrogen is now attached to the more substituted carbon, which is not supposed to happen. But in case this happens, let's look at something. This carbon over here is attached to 2 other carbons, so this is what? A secondary carbocation. Now in terms of stability, tertiary carbocation is stronger than what, or is more stable than what? Secondary carbocation, which is more stable than what? A primary carbocation. So if this happens, to achieve stability, this carbocation over here will undergo something that we call rearrangement reaction. Now we will be talking about rearrangement reaction in other videos, but just so you know, the hydrogen over here will have to move to this side, and then the positive charge will now come on this carbon, and that is the rearrangement that we are talking about. And if that happens, we call it what? The hydride shift. Hydride shift, okay? So that is, we are changing the position of hydrogen to achieve what? A more stable carbocation. So if that happens, we have our CH3 attached to the carbon over here, then we have our CH3, okay, then we have a positive charge over here, then we have C, hydrogen, then the new hydrogen that has moved here is this one over here, then we have our CH3 again. So if we look at this, we are looking at what? A tertiary carbocation over here, because this carbon is attached to 1, 2 and 3, so which is equal to what? This, okay? So we can see that even if this pathway happens, there will be a rearrangement reaction which will still form what? A tertiary carbocation, and hence this will be the product that will be formed at the end, Okay, so even though the addition doesn't go this way, in case it is an experiment, so in case it happens, the reaction undergoes rearrangement to achieve stability, and then we form just our product. All right, so let's look at more examples to understand what we are actually doing. So let's look at this. So we have CH3 bonded to what? This. By the way, this is propene, and then we are reacting it with what? HBr. Okay, so from directly we know what the Br or the bromine will be attached to the more substituted carbon, which is what? This carbon over here. So the product that we are going to get, without even writing the mechanism, is going to be something like this. Our Br will be attached over here, then we have hydrogen, hydrogen, hydrogen over here. So this is going to be the only product that is formed. Now let's look at the mechanism. So this is how it happens. So we have our CH3 bonded to our carbon bearing the double bond, and then we have the two hydrogens over here. So we have our HBr over here. So this is what? Partially positive, partially negative. So the double bond over here will attack the proton, then expelling the electrons over here onto the bromine. So we have our carbon-carbon single bond, then we have what? Our CH3 over here, and our hydrogen over here. Now this hydrogen, because this reaction goes by a Markovnikov addition, the hydrogen will attack the less substituted carbon, which means this carbon, because it has what? Two hydrogens. So we are going to have that hydrogen, this one, coming over here and then leaving what? A positive charge on this carbon. Now if that happens, we can see that this carbon is attached to what? Two other carbons. So this is what? A secondary carbocation. Secondary carbocation. Okay, now we have Br minus in solution, so it will then attack the carbocation, and then we get our product over here, CH3. Then we have the hydrogen, and then we have the bromine here, then attached to what? Another CH3. Now let's see what happens if the reaction was to go the other way around, which is not even possible. So this is the sole product. So this is our sole product. Okay, but if the hydrogen were to be attached to this carbon, let me use red to indicate that reaction just for demonstration sake. So this is not possible. Let me put, so this not possible. It means it's not going to happen, but let's just do it for demonstration sake. So if the double bond attacks the hydrogen, and then the hydrogen goes to be attached to the more substituted carbon, we are going to get carbon with the hydrogen here, then we have CH3, then single bond this H and H. So the positive charge will not be here. Now we can see that this carbon is only attached to one carbon, so it is what? A primary carbocation, which is not stable. Like I said, a tertiary carbocation is more stable than secondary, and is more stable than what? A primary carbocation. In this reaction, the most stable carbocation that can be formed is secondary carbocation. So even if the primary carbocation is formed, it is going to undergo what? Rearrangement to form what? The secondary carbocation, and then this will be the sole product that is formed. Okay, let's have a look at more examples. So let's use a cycloalkane for this demonstration. So we have this with what? CH3 here, then hydrogen here, and then we are adding what? HBr to it. So from here we know very well that we are going to get a product that looks like this. Then the double bond will go, and we still have our CH3, then the bromine will come over here, and then we have our hydrogen here as the product that is formed. So let's look at the mechanism. So by now we are all comfortable with how this reaction goes. That is, it goes via what? the Markovnikov addition. So we know our HBr, this is what? Partially positive, this is partially negative. So the double bond will attack the proton, expelling the electrons onto the bromine. So we have over here, so we no longer have the double bond. Then we have our CH3 here, and then we know that the hydrogen will go to the less substituted carbon. So between this carbon and this carbon has what? One carbon here, and then another carbon. So it has 3 carbon attached to it, but the carbon over here has only what? 1 carbon, 2 carbons attached to it. So this is the less substituted carbon. So the hydrogen will attack over here. So we have here and here. So our carbocation is formed over here. Now if the carbocation is formed over here, it means this is carbon 1, carbon 2, carbon 3. So this is what? A tertiary carbocation. It is very stable. So we have our Bl minus, which will now what? Attack the positive center of the carbocation to form our product. So we have CH3 here, the Br over here, and then we have the hydrogens over here. Okay, so let's have a look at one final example, and then we can end the tutorial. So we have CH3, C, CH3, doubly bonded to CH, and then CH2, CH3. Then we are adding what? HCl to it. So what is going to be our product? So straight ahead, we know that this is carbon 1, this is carbon 2. So the carbons bearing the double bond. And if you look at carbon 1, it has what? 1, 2, and then 3 carbons around it, okay? But then this carbon has hydrogen and then 1 carbon attached to it, okay? So it means this carbon 1, is our most substituted carbon. So it means our what? Chlorine will attack this carbon. So we have CH3, C, CH3 at the top. Then we have our chlorine attacking this carbon. Then we have C, H. Then we have the CH2, CH3 here. Then we have our hydrogen coming over here. So let's write the mechanism for this. So if we have our compound over here, CH3, doubly bonded to C, H, CH2, CH3, our HCl will come in this form. This is what? Partially negative, what? Partially positive. So the double bond will attack the proton, expelling the electrons onto the chlorine. So we form our what? Carbocation. So we have CH3C, CH3, single bond C, H, CH2, CH3. Because this carbon is the less substituted carbon, the hydrogen will attach itself over here, and then we have the carbocation over here. By the way, this is a tertiary carbocation. So we have the Cl minus still in solution. It will now attack the carbocation to form the product that we have over here. So we have CH3 attached to the carbon CH3. Then we have the chlorine over here. Then C, hydrogen, hydrogen. Then we have CH2, CH3. So this is how we do the what? The hydrohalogenation of alkenes. And then one thing we need to know is that this reaction, in terms of what? Regiochemistry, that is the point of attachment of the species, goes via what? Markovnikov addition, Markovnikov's addition. That is, the hydrogen goes to the less substituted carbon. And in terms of what? Stereochemistry, it doesn't show any stereochemistry. That is, you can add the bromine or the hydrogen to either side of it, either both syn or anti, it is still the same. So thank you so much for watching, and I'll see you in the subsequent videos. Bye bye.